Hello, everyone. My name is Friya Hussain. I'm a research fellow at the Department of Chemical Engineering here at UCL. Today's talk about the discover acoustical in engineering. And let me start with it that acoustics itself is one branch of physics, which is deal with the study of mechanical waves in gas, liquid, and solids. That include the topics of sound, ultrasound, and the vibrations. The study of acoustics revolve around the sound generation, the propagations, and the reception of the sound. There are many different applications of acoustics in different areas, such as in engineering, earth science, life science, and arts. There are different methods of, there are different techniques of the acoustics as well, such as electroacoustics, which is used to reproduction of the sounds in instruments such as mobile phone. Ultrasound, it is a special acoustic technique with a frequency above human hearing, which is used in medicine for medical imaging. We use it in engineering for measuring the volume fraction of solid particles or droplets in multiphase flows. We use it for measuring the particle velocity profiles and the size distribution of dispersed phases in particulate flows. There are other techniques used, such as the underwater sound used to monitoring the temperature, to monitor the climate change just by measuring the temperature in water, and then bioacoustics, which is used in for analyzing the hearing in animals and also in medicine. So mostly in engineering, we use three different acoustic techniques. One of them is ultrasound, another one is the vibration, and the last one is acoustic emission. Ultrasound is a mechanical wave with a frequency above the hearing, so human can hear between 16 hertz to 16 kilohertz. Above that, which is we call ultrasound. Vibration is when you apply the ultrasonic pressure to a medium such as a liquid, the ions vibrate and generate the electric signal that can be used to analyze electrolytes. Acoustic emission is related to a sound generated by movement, by vibration or friction or cracking, an event happen. Then you record this sound and analyze what will happen. So ultrasound is dated back to 17th century when the Italian scientist Spallanzani were able to demonstrate that bats can actually navigate their prey by using the ultrasound, sending the ultrasound pulse and record the echo reflection of the ultrasound and navigate their prey. And later in 18th century, there was the Swiss scientist who used the underwater bell to measure the sound speed in water for the first time. And late 1940s, there were more attention of using the ultrasound for medical imaging. And the first diagnostic imaging was done by Carl Dosk in 1942. So all acoustics is, which is, as I said, is mechanical waves. That mechanical waves have different frequencies. The frequency with a range below hearing we call infrasound, just below 16 hertz, between 16 to 20 kilohertz, which is we can hear, that's we call audible sound. Above that is we call ultrasound, that the frequency, the sound wave with the frequencies that we cannot hear. So what is a sound wave property actually? Sound wave is propagated in two forms. One is longitudinal, one is transverse wave. So if you see the image here, you can see that longitudinal is just like a spring. You pull it out and release it. So the wave propagation, the particles vibrate parallel to alongside the propagation direction of the wave. But for the transverse wave, the particle propagate at the right angle of the wave propagation. So mostly we see the wave as like a sine wave for even longitudinal and also transverse. It's just the way we interpret it for us to easy to understand. But actually, what is in reality look like, the red one is longitudinal wave and the blue one is the transverse wave. Longitudinal wave can travel through different media such as gas, liquid, and solid. But the transverse wave can only travel through a solid media. So these waves have amplitude, it has frequency, and also the speed of propagations. The wave propagation speed is different in different media. So let's first see what ultrasound methods we can have, and then we talk about the wave speed, amplitude, and also the use of them. So in engineering, we use three different methods of ultrasound. What we call transit time is the time when the ultrasound propagates from the sound source, like as we have a transducer, and then reflected back by the particles or objects or end of the pipe. Then we record the signal. The time that signal travels and received by the receiver, we call the transit time. This we use it to calculate the sound speed, how far the sounds go. We use it to calculate the volume fraction of solids, droplets, or bubbles in a media, or you can use it to detect the object, how far the object is from you. Attenuation is when the ultrasound propagates from one media to another media, it loses its intensity in the form such as some of the energy of the sound wave converted to heat, some because of when it meets different interfaces, some of the sound wave reflected and some of them will transported. And if the meat is a rough surface or sharp surface, the sound wave will scatter and also lose the amplitude. That we call attenuation. So for example, if you do have a system, we want to measure the concentration of particles inside. When you send the signal through the mixture, the sound wave scattered when it meets the different particles or bubbles, and then you calculate the attenuation to know how many particles you have in a system. Another method we do use in engineering is Doppler effect. So a simple example of Doppler effect is that when you standing in a point and an ambulance come towards you, you hear the noise of the ambulance louder. But when it passes you and you see you hear the noise level is going down. This is because when the ambulance come approaching to you, the frequency of the sound you receive is increasing. And when the ambulance move away from you, the frequency of the sound you receive is decreasing. This is called a Doppler effect. We use this concept to calculate the velocity profile of particles, droplets, and bubbles in solid, liquid, and in multiphase flow medias. So back into the sound speed. So why sound speed is different in air compared to water and solids? I mean, it's like I see the sound wave speed in air is 340 meters, and in water, in fresh water at 20 degrees is 1,480 meters per second. And in some sort of solids will go up to 5,000 meters per second. Why is that? It is because the way their molecules is formed. In air, the molecules are far apart from each other. So it takes time for the sound to heat one molecule to the next one. But in water, they are closer, but still there's a gap between them. But in solid, they are more compacted together. So it's easier for sound to heat from first molecule to the second molecule. So that's why it moves faster. So these variation of sound speed in different media, it depends on the density of the medium as well. So these help us to recognize, to understand what kind of materials we do have by measuring the sound speed in a material, because it depends on the density and a property of the chemical property of the materials. So how do we measure the sound speed? I'm showing you an example here, which is I did in our lab here at UCL. This is a pipe flow contains water, and this is ultrasonic sensor with a gel attached to the pipe wall. So as I said, when the sound wave propagates from one media to another media, it will reflect when it meets each interfaces. As you can see that this is a signal. The first one is a signal where it's generated inside the sensor, and then when the signal is just propagates through the gel and then meets the first interface of the pipe. This is the first edge of the pipe, and then goes, when it meets from the pipe to water, because it's different media, some of the sound is reflected, and that reflection, it depends on a density. If the density of the first medium smaller than the second medium, such as the first one you see here, is the reflection is larger. But if the density of, like say, water is smaller than the pipe which is made from acrylic, the reflection is smaller. So you measure the sound speed travels through the pipe until to the end and reflects it back. That we call the time of flight. So the red color here is the sound travels through the pipe wall, and the green one is reflected. So we measured the time when the sound wave takes from from edge of the pipe to another side of the pipe as 34 microseconds. And we use this simple equation, which is C is the sound speed, D is the diameter of the pipe, which is 2.6 centimeter. TRF is the time of flight, the time when sounds go through. The factor number 2 is because the sound wave, it goes and come back twice. That's why we use the factor number 2. And we measured the sound speed in liquid or is in tap water, and it's 1,518 meters per second. So you can use a similar method to measure sound speed in multiphase flows as well, in solid liquid, in liquid, in different materials, and to analyze their properties. Another property of the sound wave is just the signal is attenuated while it travels through one medium to another medium. That's how that it's happened. So when the density different between two media, the sound wave partially reflected and partially moved. If the particles smaller than the wavelengths of the sound wave, then the sound wave will be scattered. If larger, the sound wave will be reflected. So in that way, you lose the ultrasound lose some of its intensity. So here I just measure the attenuation in solid liquid media. So how you do that? First, you send the ultrasound wave by this sensor through the liquid phase only when you have only liquid, and receive it by the second sensor. And the signal is look like this when you see it, that the amplitude of the signal and the time of the signal travel from this point to this point. So we send the same signal through the mixture of solid, when you have a solid particles inside the liquid. You can see how the amplitude of the signal is attenuated. Is that because this ultrasound scattered by these particles inside the solid liquid media. So the larger number of particles you have inside, the larger number of scattering it happens. So when you have larger number of scattering, the higher signal will be attenuated. So this concept can be used for measuring the volume fractions of these particles inside the solid liquid media. So how you do that? You simply use the attenuation coefficient equation, II, which is the attenuated amplitude. I naught it is an initial signal, alpha is the attenuation coefficient, and X is the pipe diameter. So you can use this method to measure the particle size and also measure the volume fractions. We did that, and I will show you how we did it. To start with the basic principle of ultrasound imaging, this is very important for you to understand how ultrasound imaging is worked, and for you understand the ultrasound signal, and you can apply to different systems. So simply, this is a container contains droplets and water. This is a wall of the, let's say, the pipe, and you have an ultrasonic sensor attached to it. Use the ultrasound gel between the sensor and the pipe wall to reduce the air trapped between the sensor and the pipe wall, because the ultrasound is highly attenuated in air. So you send the ultrasound signal through this droplet and water mixture. The signal will pass through and reflect it from the pipes and then enter to the water. And then when it meets each particles, the signal will be reflected. It depends on the size of the particles here, or the volume fraction of the particles you have it. The signal is reflected. So what the sensor does is tells you that the time when the signal travels and what time when the signal is reflected. So based on the previous equation here, this equation you can find how far the particles from the edge of the pipe or the sensor, and then you can do the imaging. So this is the typical signal of this system. As you can see that the first two peak of the signal is that signal reflected from the first and second edge of the pipe wall, and then it's silent. There's no reflection here because there's no particles, only water. When it meets the particles, the signal starts to reflect it. It depends on the particle number and the particle size. If you draw the time domain frequency of the signal, you can see on the right side here, this bright line is the pipe edge, and this is the dark area is just water, and the bright area is a reflection of number of particles. So this is a basic principle how the ultrasound imaging works. So as previously I was talking about the transit time and attenuation and also the Doppler effect. What you can use each of them for that. For example, transit time you can use to detect the object, how far is from you, or how far from anywhere in a system you measured. You can use it for a size measurement. You can use it in battery to detect the state of charge, because as you know that when the battery charge is decreased or failure, the chemical property of the battery is changed. Therefore, the time of flight, the time when the ultrasound propagates from one side to other side in a battery, it will change. You can use this way to analyze the state of charge or the state of health of the battery. Ultrasound is safer to use and easy and cheap to set up. So therefore, is a good way to monitor the state of health in the battery. We use it as a flow meter here to measure the flow velocity. So basically, we use two sensors in a pipe flow to measure the volume flow of liquids. How we did that, I will just show you how we did it. So we had a pipe flow where water flows from left to right here. We send the signal from transistor 1 and receive it by the transistor 2, and then from transistor 2 to transistor 1. How does it work? So when the ultrasound wave propagates from transistor 1 to transistor 2, it goes against the direction of the flow. When the sound wave goes against the direction of the flow, the wave is deaccelerated, and therefore the speed of sound decreases. When we send the sound wave from transistor 2 to transistor 1, the sound wave accelerated, then the sound speed is increased. So by measuring the time difference, the time where the signal takes from 1 to 2 and the time where the signal takes from 2 to 1, you were able to measure the flow velocity. So the image in the middle here shows that the signal we receive it from each sensor. The red one we receive it from the sensor 1, sensor 2, which is go from top to bottom, and the blue one we receive it from the sensor 1, which is go from bottom to top. So as you zoom in out this signal, you can see that the red signal takes a little bit more time than the blue signal to travel. That because it goes against the direction of the main flow. Using these two simple formula allow you to calculate the velocity of the flow. So D is the diameter of the pipe here. C is the sound speed in liquid, that's what we have in water here. V is the velocity of the flow, the mean velocity of the flow. Theta is the inclination angle of the sensor. So by measuring the time up and time down added to this equation, you are able to measure the flow velocity. This is flow rate measured in pi flow. The x-axis is measured by the rotameter, and y-axis is measured by the ultrasound. So how do we use a ultrasound speed measurement and attenuation to calculate the volume fraction of solid particle as an example here? What we did is we basically first send the ultrasound through the liquid phase only. We take as a reference, we measure the sound speed in liquid, and then we send the ultrasound speed through the mixture, which is we have here is solid liquid mixture. And then we measure the sound speed. So the variation of the sound speed allow us to calculate the volume fraction of the solid particles. And in this graph, you can see that when we increase the flow velocity here, this is basically a fluidized bed. So the bed is the particle is packed here. When the water flows, these particles start to expand. The more it expands, the less the volume fraction will be. So as you can see that where this is a velocity increase, the blue one. When you increase the velocity, the bed is expanding more, and you have less volume fraction. As you can see, the attenuation is decreases because you have less number. When the bed is more expanded, you have less number of particles within the range of area of the sound wave propagated. And here we use the ultrasound speed to measure the voidage of the bed, which is when you increase basically the flow velocity of liquids here, the particles more and more expand, and you have less volume fraction. So what will happen is when you have less particles, the velocity of sound will decreases, but when you have more number of particles, the velocity of sound increases. Why is that? Because the sound speed is larger in solid compared to liquid. We did the same setup to measure the volume fraction of droplets in oil and water flows. So we had a pipe wall with 2.6 centimeter in diameter, and the oil and water, the two liquid phase flows, and we send the signal from via one transducer and receive it via the second transducer. The typical shape of the signal we receive it here, as I explained it in this image. So you do have this is a stratified flow. When you have the oil and water, between the oil water, there's an interface. Some of the oil and water that will be mixed. This is picked up by the ultrasound as well, because the density difference between oil and water, and then water. So what we did is we measured the sound speed first in a liquid water phase only. Then when we mix oil and liquid, we measure the sound speed in a mixture. So this is sound speed in water only. As you can see that is about 1,580 meters per second, but in crude oil, because the density is smaller, is about 870 kilogram per meter cubic, which is that's why the sound speed is smaller. So then when you have a mixture, you measure the sound speed in a mixture and compare it to these sound speeds. Then it allow you to calculate the volume fraction of droplets or volume fraction of oils, or if you have a three-phase, even the volume fraction of the gases. But here we have only two phases. So you can see that the ultrasound speed decreases with increasing the oil volume fraction. So you can use this technique to measure the volume fraction of bubbles, particles, droplets, and liquid, and so on in different systems. You can use it in stirred vessels, you can use it in fluidized beds, you can use it in pipe flow as well. The most interesting techniques of the ultrasound is Doppler velocity profiling, to measure the velocity profile of particles in multiphase flows. So how that happens? When you have a sensor attached to the pipe wall with inclination angle, and then you propagate the sound wave through the mixture. When the sound wave interacts with each particles, the sound wave scattered. It was due to the different interfaces between the particle and a liquid phase. So the scattered signal is shifted in frequency, which is different from the frequency of the source we send it. Why? Because the particle is moving. Remember when I said when the ambulance come approach to you, the particles, the sound become louder. When it go away from you, the sound level become lower because of the frequency change. So here is the same situation. When the particles move towards from left to right towards the sensor, the frequency of the reflected signal shifted is larger than the frequency of the signal we send it through the mixture. So that we calculate this frequency shift to measure the velocity of the particles. If the particles move towards the sensor, the reflected, the scattered or frequency is larger than the signal frequency we send it in the beginning. That meaning that we have a positive Doppler shift. The Doppler frequency is calculated using this equation. FR is a scattered frequency where the signal is scattered by the particle. F naught is an initial frequency where we send it. But if the particles move away from the sensor, well, let's say in this point, if it go to the left side, then the FR, which is the scattered frequency, is smaller than the F naught, which is the initial frequency. Then the Doppler frequency will be negative, which tells us the particles move away from the sensor. In that way, we can also calculate where the particles go right or left, and how fast the particles go as well. So the faster the particles go, the higher the frequency is shifted. So based on this concept, we are able to calculate the velocity profile in multiphase flows. So previously, this image on the left, you can see one transducer is used. Previously, one transducer used by the researchers to calculate the velocity profiles. But we come with the idea to using two transducers. A good question to ask, why one transducer is, why two transducer? Well, when you use one transducer sends the signal and switch it from the transmitter to be a receiver to receive back the signal. It takes some time. And during this time, the sensor will lose some of the signal. But here, when you use two transducers, one just sending the signal continuously and the second one just receiving the signal. Therefore, you do not lose any sort of the signal. We did measure the velocity profile of solid particles in solid liquid fluidized beds. How we did it, we set up the signal and send it through the via the sensor through the mixture, and the signal scattered by the moved particles, and we receive it by the second sensor, by the receiver, in this form. You can see that the difference between these two signals. It is because the signal is scattered by all these particles moving in this area. That's why you have a number of scattered pulses. Then the frequency of this scattered signal, it is in this form. To calculate the Doppler frequency, you detect the initial frequency of the sound wave you send it through by this equation, and using the fast Fourier transform to analyze the to extract the frequency spectrum. When you have the Doppler frequency, you feed it to this equation to calculate the velocity profile. C is the sound speed in a mixture here. Theta is inclination angle of the transistors, and F naught is initial frequency you send it. FD is a Doppler frequency. This is a fluidized bed I'm talking about. This is solid liquid. A particle is moving up and downward. They won't go anywhere. They're just moving around, moving up and down. And we're using this technique to measure the velocity profile of these particles. And we were able to calculate the velocity profile of these particles, and based on the Doppler effect principles, will tell us the particles in the center of the bed moving upwards and down on the sides. We calculated the velocity profile for different flow rates here. That's done with ultrasound compared to other techniques that is almost impossible. Another measurement we did with the ultrasound technique is measuring the particle size distribution, which is a very interested to scientists working in fluid dynamics. So what we have the same fluidized bed with contains glass beads, and then we send the signal through the mixture through the liquid phase first. We took as a reference signal, as I earlier explained how to measure the attenuation, and then we send the signal through the mixture of the solid liquid, and then we recorded the signal passed through the mixture. For measuring the particle size, it is important, and also it has to be the signal you send it through the mixture it contains various frequencies, at least more than 3 different frequencies to calculate the particle size distribution, because the attenuation is also a frequency dependent, and when you change the frequency, you change the wavelengths of the sound, therefore you're able to measure different particle size. How you do that? First, you send the signal and record it and measure the reduction in amplitude using this equation. This is a attenuated amplitude. I naught is the initial amplitude of the signal here on the left. Alpha is attenuation coefficient, X is a pipe diameter. Then you measure the attenuation coefficient for each frequency. Here we use it 7 different frequencies, 2, 3, 4, 5, 6, 7, 8. So for each frequency, you see when you increase in the frequency, the attenuation is increased more as well. Why? Because when you increase the frequency, the signal is more oscillate and lose more its intensity. So then you need to invert the measured attenuation to a particle size distribution. There are several inversion algorithms available, such as optimum regularization techniques, genetic algorithms. They can be used to invert attenuation to a particle size. So we pour 3 different samples, each time one sample enters the bed. We measure the particle size, as you can see that. The red one for the small particle size, blue for the medium, and black for the large one. And lately, we mix all these 3. We mix all these 3 and pour them in a bed again. And then using the same technique with ultrasound, and we were able to measure the particle size distribution of all of them. We did the similar way with similar technique, used a similar technique with the oil liquid flows to measure the droplet size distribution. We use the same, we send the signal through the mixture, we record it, and we measure the attenuation coefficient of the signal for various different frequencies. And then how we did, we changed basically the flow rate of the water and oil here, and then each time we measure the different attenuation of the sound happen because of the increasing the volume flow of oil here, and then we measure the attenuation. So the simple technique is that you firstly only send the signal through the liquid phase only, you record it as a reference, and you send it through the mixture, and you compare them to calculate the attenuation. And then use this equation to measure the attenuation coefficient for each frequency. You make sure you have more than 3 different frequencies to calculate the particle size distribution. And then you use the inversion algorithm. It will allow you to invert this attenuation coefficient to a size distribution. So we use ultrasound technique here to measure the particle size distribution, the droplet distribution. You can use it for the bubble size distribution as well. So the second technique is more advanced. I'm talking about here is acoustic emission. The difference between acoustic emission and ultrasound is that ultrasound, you generate the signal and propagates through the mixture and you record it. But in acoustic emission, you do not generate the signal. Basically, the signal is generated to do the event happening. For example, reflection, collision between particles and droplets, or pipe wall, or even or cracking. This, imagine when two particles collide with each other or collide with a pipe wall, they generate an energy in a form of elastic waves with a frequency in a range of ultrasound that we cannot hear. We use an acoustic sensor to record that signal and analyze the particle size, for example, the velocity of the particles colliding, or the event. The signal of the acoustic emission look like this form, is always a pulse signal because it's abrupt signal. It's let's say it's not possible to be a continuous signal because the average time of between the bursts of the emission is less than the duration of the signal itself. There will be a pulse signal. So that signal has amplitude, duration, and rise time. The energy of this signal or the amplitude of this signal, it depends on how large the particle is or how small the particle is colliding with each other, or how fast they do collide with each other. So we use these parameters to analyze, for example, particle size in solid gas flows. This is a system we called solid gas fluidized bed. It contains the particles. The air flows from the bottom to top. The particles start to move and collide with each other on a bed wall. And these collisions generate a sound in the form of elastic wave with a frequency range of 100 to 1 megahertz. And this sound generated via these collisions recorded by the acoustic emission sensor. And we use the sound to analyze the particle size here. So we used 4 different samples. Each time you pour one sample into the bed and we record the acoustic signal. The acoustic signal is in the form look like this blue one we recorded. We filtered the signal to read of the noise, background noise in the area was 20 kilohertz, and then measured the acoustic energy and inverted the signal to a particle size. So let's say you have a system, the particles colliding, the signal is generated and recorded by the sensor, and we have a signal like this. And how we do it? We use a fast Fourier transform to have the amplitude of the signal for each sample. What we found that is the amplitude of the signal is larger for larger particles and smaller for the smaller particles. That's possible. Imagine you collide 2 small particles with the same speed and 2 large particles with the same speed. The 2 large particles generate higher energy compared to the small one. So this is similar way. So how do you measure the energy of the signal? You use this equation. Fs is a sampling frequency of the signal. AI is amplitude generated of the signal. And then you calculate the energy. We do have the inversion algorithm, this one, which is these terms are constant. E is the energy, and V is the velocity of the particles colliding. And we use this inverted algorithm to invert this energy to a particle size distribution. And we were able to measure particle size for 4 different samples, as you can hear, in 100 micron to 250 micron, 250 to 355, and then 500 to 700. As you can see here, based on this method, we were able to measure the particle size distribution in solid gas flows. So that technique could be used to measure the velocity of particles impinging with the bed wall or colliding with each other and other parameters. And lastly, another techniques I was talking about is vibration. So the idea is come from when you send a sound wave through the electrolytes. It contains ions, cations, and anions. The sound wave make these ions to start to vibrate. Before you send the sound wave, the ions, cations, and anions are there, and they're just satellites. When you send the sound wave through the electrolyte, you vibrate these ions. When you vibrate them, you displace them. When you displace ions, it creates a dipoles, number of dipoles. Each dipoles will generate a potential in the form of electric potential. If you attach two sensors to the system, you record this electric potential and can be used to analyze the fluids, ionic fluids. So firstly, I modeled the system when you have different fluids, and then recorded the signal. Why I did this? Because I was curious about that current ultrasound imaging we're using in medicine, in hospitals right now, not able to image the ionic fluids in human body, but while we use in ultrasound, can we image the ionic fluids, but in different way. So what I did is I had I made it from the agar gel, contained some ionic electrolytes, mixed with the gel, and used the Mindray machine, which is a sonography machine in hospital, to image the sample, the body. As you can see that the medical image device wasn't able to pick up this sample here. You can see it's nothing, it's clean. The signals look like that, it's flat. But the device I built it is, it works like when you send the ultrasound pulses through the mixture, when contains electrolytes within the body, these electrolytes start to vibrate, and you displace them and create dipoles and generate potential. You use two sensors attached to each side of in parallel of the body. I'll pick up the electric signal. As you see, the signals look like this one. This is the signal generated from the electrolytes, where you don't see it in current conventional ultrasound imaging. So proved that this device were able to image the ionic electrolytes within tissue, human bodies. So lately, I went to the butcher, I bought some meat, the pork meat, I put it inside the bath water and sent the ultrasample through it, and attached two sensors to the end to image the tissue. The first image on the left one is recorded by the device I made it. It picked up 9 different features inside this tissue: liquids, fats, muscles, all of it. The right one is the signals from the conventional. When I say conventional ultrasound imaging, the machines we use it currently in medicine, it works based on a reflection. So this is a reflection imaging. You can see that only picked up 6 different features. So why, and also the signals go attenuated, the files go and more attenuated, and you don't see it. So with this current ultrasound imaging we do have, you only able to detect the surface with different interfaces. And the farther the signals go is more attenuated. Sometimes you even not see the deep inside. But the device I made it was, it also see the interfaces and also the electrolytes, the fluid inside the body that image actually the fluid inside the body. This can be a huge improvement for the medicine, rather than they go to, if they want to test the fluid inside the human body, they will inject it. If this one build it up for the machine to be used in medicine, that will be a huge improvement. So I used this in different electrolytes to measure the atomic weights of the electrolytes to recognize different ions. I use it in colloidal suspension to characterize the charge density in colloidal suspension as well. And that's all from me today, and thank you very much for your attention. And any questions here? Okay, if we do not have any questions, I think thank you very much for your attendance today and your attention.